Stop. Stop.
Acting terrible. Oh my, get out of the way, please. All the humanity and all the fantasy.
Did you know that when Orson Welles did the radio play of H.G. Wells's War of the Worlds,
Right.
he studied the vocal intonations of that announcer
You're kidding me.
and copied them for the announcer who saw the aliens,
Making everything sound that much more dramatic and tragic.
and real and scary. You ever notice when it launches, a few seconds later, it executes the what?
The roll.
The roll program. What I'm about to describe is true for everything that goes in orbit. Half the energy of that rocket is not there to get it up into space.
Half.
Half the energy is to take it downrange.
Aha.
That's why every rocket you have ever seen launched doesn't just keep going up.
Right.
Ever stop and wonder?
When I was younger and I would watch these launches because they were such a big thing and you had to watch them even in school, I used to think, well, they're never going to make it to space. They're going sideways.
Thank you. That's an observant point to make. So it goes from 0 miles per hour to 18,000 miles per hour sideways.
Nice.
Because once the rockets stop,
Right.
does it fall out of the sky now?
No.
Wait, it achieves orbit. So what is orbit? There's that one magic speed where you are going so fast downrange that you are falling to Earth at the same rate that Earth is curving away from you. And Isaac Newton first demonstrated that, and that is the definition of an orbit. You don't need rockets. You will stay in that configuration. So my only point is, so many people look at rocket launchers and think they're going up into space.
Right.
When what we call space in the 0G environment, when people go, is orbit.
Right.
You go into orbit around Earth, and they're not very high above Earth's surface. Couple hundred miles. That's it. That's the distance from New York to Boston,
Yeah.
or New York to Washington, D.C. You could drive that distance in 4 hours,
Yep.
obeying speed limits. It's just something that people might not have noticed. Now, if you're not going into orbit, then all of your energy is going to just go up, and then you just drop back to Earth. The Bezos-Branson billionaire boys race. Okay.
Bezos Branson's Billionaires Boys Race. That's
Boys
amazing.
race, okay.
I love it.
All right. Elon went into orbit.
Right.
My man Elon knows what orbit is.
He knew that he had to get out of here. He
He
knew.
needs an escape hatch.
He was like,
They're coming after me. They're coming after me.
I'm planning for the future. I'm going to find a way to get out of here. I'm planning for the future.
When the pitchforks are coming.
That's it. Bezos and Branson, they can come back. They got a place to come back to. I know. I got to go.
So they, Bezos and Branson, what they're doing is they're going up and then shutting off their engines and just falling back to Earth.
Right.
They land in the same place they took off from. All right. So they didn't go downrange at all. They did not go into orbit. So they go up and then they fall. And while you are falling, where there's no air molecules, which is that famous Kármán line that they reach, you drop you from there, you are weightless. I'll tell you one last thing, which is completely obscure. It's for physics geeks out there.
Okay.
There's something called the brachistochrone problem.
Okay, now you certainly are going deep now. This is a deep cut on the B side.
Let's have a round ball
Right.
at some height, and it wants to get to the bottom of a hill. The question is, what shape should that hill take so that the ball gets to the bottom of the hill fastest? If you make the hill just a straight line from where it is to the bottom, okay, it'll roll down and it'll get there.
Yes.
But if you make the hill drop first and then curve out the bottom, you can get some serious speed here and that puppy will roll out fast. Okay? This is called the brachistochrone problem.
Nice.
And it requires sort of Hamiltonian representations of the energy of the system to solve it. Okay? The Bernoulli brothers posed these to each other. They were two math brainiacs. Anyhow, the solution to this problem is first a pretty steep drop, before it curls out to the bottom. And that will beat the straight line every time.
Of course.
That curve, if you flip it up, that is the trajectory to launch your rocket.
Oh, watch out. Yo, that is a physics mic drop right there.
Oh.
Yeah.
So that's how to get into orbit the most efficiently.
It's very elegant, by the way.
Yeah, and it's just an interesting question. When you're curious and you're mathematically literate and you know a little bit of physics, these questions come up in your life, and you're compelled to solve them, as the Bernoulli brothers did.
Nice. Oh, those Bernoulli brothers, you know, they were something at a cocktail party, that's for sure.
The life of the party. Yeah. So, unfortunately, they never knew that this was also a rocket.
Hello? Hello?
Hi, Christopher. Hi, how are you?
I'm good.
Okay, Happy New Year.
Yeah, Happy New Year.
All the best. Thank you. Okay. All right. So today we want to do a lot of questions. We did mostly more theory last time. So there's a couple of papers. And if there's time, we can still continue with the theory. Yeah? So, okay, so we have one question left from last time from this type of questions before we go into the papers. And I would like to start with this one. So we go back to polarized light. And what is meant by the plane polarized light, or a plane polarized light wave?
Allows only light waves with a certain amplitude and it only allows light waves with a certain angle.
Okay, yeah, may say so. When you look at the word plane, there's a certain hint here in the answer actually, or which you can use for the answer, which is along with what you just said, but just utilizing the word plane as well to link it. When you think of the wave, right, it's an oscillation, a vibration. When you have unpolarized light, in which directions do the vibrations go, the oscillations?
Perpendicular.
In an unpolarized, just that when you look at the sun, for example.
It's at every angle.
Exactly, yeah, exactly. Yeah. Just any direction actually, or any imaginable plane, if you want to say so, right? If you think that, of course, you can always think X, Y, Z, but theoretically we could define any in between as a plane on its own as well, just in a certain angle to the X, Y, Z, for example, right? So when we now look at the polarized light, what is the situation in terms of a plane? Which links to what you said with about the wave at the beginning. So when you have the origin, right? So you basically, well, that's of course not really 360, but basically we can have any like that, right? All of that is a plane, right? If you want to say so. But yes, depending on the origin of our coordinate system, then of course it has a certain angle to the origin. Otherwise, it's just an infinite, basically, well, kind of an infinite number of planes. If you take a 360 approach, a spheric, then of course you may say, well, every 1 degree, I have another plane, so to speak. But in theory, you could divide it into infinite number of planes, right? But after the polarization, how many planes are there left?
One.
Just one, exactly. No? So that's where I wanted to see the link, right? It's correct what you said with the one wave. So basically, it just allows, but it's a different way to say, the oscillation only to be in one specific plane. So of course, that now this is a bit too limited. That looks like one-dimensional. But of course, if we say this is many planes here, then of course they can be many accordingly in the various angles, whatever. But in the end, there's only this one. And of course, it can only oscillate in that way, in that plane, so to speak. Okay, so that's another way to explain it. Then to question B. Which it doesn't matter if it's the light reflected from the surface of water. It could be any at the end of the day, right? It's just about the basic idea of how can you show what happens when you have a polarized situation or a polarized plane. How can you demonstrate that? Of course, using a polarization filter, that is something you would have to include, of course, otherwise you can't show it. So how would you show that polarizing effect? Going back to what you said for what question A as well, you can just use that as well, actually. But then not look at it as a static situation. So that one plane, what would you do with that one plane or with the filter actually to show the polarization effect?
I don't remember.
So say again, Chris?
I don't know.
Okay, no, that's fine, no problem. Right, when you think of it, you said it. When you have how's the plane, the angle of the plane to the axis, in order to get the best effect, let's say it. So if we say this is, well, that symbolizes the unpolarized light source, right? And we have something like this as one direction of travel, just from one specific light. And then we say well, that's not three-dimensional, kind of. So then we say, okay, I have an axis here, right? And I call that, and I could make it dotted as well, actually, maybe better. Illustrate it a bit better. So what is the typical angle between the direction of the travel? And this is the and this is the transmission axis, right? And what is when is the best effect? I mean, you basically said it before in A. When is the best effect of the polarization? When you look at the transmission axis and the travel axis or direction.
90 degrees.
Yeah, exactly. So something like that. Huh? So when we have that angle of 90 degrees, well, this is now not really a nice picture, but you get the gist of it, right? And that is the Polaroid, of course. So when we say, okay, when you have it 90 degrees, what is then the minimum of the light passing through? At which angle? So when you think of the Polaroid as the filter, right, and you have it in the 90-degree angle, so then you will just have one plane of polarized light going through, right?
Yeah.
So it basically can show it like that, right? So this is the polarized light. So this is what is left. So basically in that context, we basically say, okay, this one makes it through. Of course, I could organize it differently, but this is just an example. So it goes through, henceforth, I have the effect. Is that now the minimal effect? I mean, of course, it depends on the question. When we look at the polarization effect, is that the maximum effect in terms of polarization or the minimum effect? What would you say in terms of having the effect you want?
Maximum.
Yeah, exactly. So in this case, you have the maximum effect of the polarization, right? Which means as only this particular part goes through, when you now tilt your Polaroid and make it at a 0-degree angle, what happens then?
Nothing goes through.
Um, Let me see. So if that one, the Polaroid, is now being tilted, so it basically in the end it ends up like that. Is there any effect?
The height, the
Basically,
amplitude is decreased.
amplitude is not necessarily affected. Could be, but that's a different question actually. It's just like, okay, now we have this 90-degree angle, and now we start to tilt the Polaroid, right, until it's plane like this. So it basically it's in the XY axis, so to speak. No more said. Is then the effect? What is the effect of the Polaroid in that moment?
It only blocks the horizontal.
Yeah, if there's any, exactly right. So it's difficult to imagine because it will be very, very thin. So it basically hardly blocks anything, right? I mean, it's a good comment, but if you think about how it's organized with the long chain molecules here, and then you have a wave coming like that. So it's difficult to there will be no effect basically, right? Because it's infinite thin. The moment it has a certain thickness, it's a different story, of course. So basically, what you have is the maximum effect is clearly when it's in 90 degrees, and the minimal effect, or near zero, is when it's well, like that, in a 0-degree angle to the travel direction, or in a 90-degree to the transmission axis. It really depends on how you define it, right? Or if the angle between the transmission axis and the travel direction is 90 degrees, you have the max effect. If the angle between the transmission axis and the travel direction is zero, that means they're in the same plane, hence you have basically no effect. That is how you can demonstrate that, because you would have a min and a max effect basically, depending on the 90-degree variation, right? And it would look, actually, we have a similar question again, so I'm not drawing it, because in that question, you will have to draw it. So there will be basically from, depends on, again, what you ask, maximum throughput or minimized throughput, then you have accordingly the effect. Huh? Now, when you go into C, so we have the vertical plane, right, is incident on 3 polarizing filters. And the transmission axis, so we have 3. Now that's of course something which you would have to draw something, right? We have 3 filters actually, also 3 Polaroids, P1, P2, P3. And it tells us that the transmission of the first Polaroid is vertical. So how would I have to see that?
First one is normal.
Okay, yep. So we can just say something like that. The second one is tilted, right? Sorry, that should have been in a 45-degree angle. And the last one is in the plane, huh? Like that. So gradually from 90 to 0. Is that okay? Yeah. Okay. This is the same. So now we're talking about the intensity of the light. And we want to say it's not 0. So what we say is the intensity is not 0. That's what I claim. Huh? Now I have to show that. So when and of course I have my source here. So what is after P1, P2, P3? How is the intensity after P1?
The highest.
Okay, so if we say this is intensity 0, will it be identical?
Yeah.
Exactly, huh? All right, so that's in situation after P1. After P2, how will that be? How's the relationship in the polarized intensity situation? Or how's the link between the intensity involving an angle? It's that.
I think it's sine.
Nope. Why is it not sine? When you think that you gradually start to tilt it, and which is the angle, of course, that's a key question. Which one is the angle? I mean, theoretically it could be sine, but by agreement, let's put it, the gentleman who put that into a law started measure from which axis? So if we introduce theta, so what is the angle of theta here in the first case?
0.
Okay, so if the angle is 0, henceforth, can it be cos or sine? Or does it have to be? Which one does it have to be?
Sine.
But then it would be 0, right? I mean, the law has to apply for every angle. It's just a matter of which value. So if we write it like that, and then we say it's related to theta, we know it's a square relationship, but we can put that aside just for the first consideration and say, okay, if I have sine, what is the sine of 0 if theta is 0?
0.
Exactly. Huh? So, I mean, that's always an easy cross check, right? I mean, in the end, it's a matter of where you start. But as the angle starts here and then goes down, so to speak, theta goes downwards, or better said here, actually, it's not easier to show. And of course, from the original one, of course, is 90 degrees, huh? And here it's 45. So we measure it against the vertical axis, actually. So henceforth, it must be sine. But is there anything else I have to reconsider when I'm looking at that, the relationship of that law? It doesn't matter, of course, if it's equal to, but if there's an angle, let's say here, so I'm having sine of obviously 45 degrees. Anything I have to consider additionally to make the law complete? And why do I write sine now? Excuse me. Do you remember, Chris?
Um,
Is it just cos or maybe something else? Or
squared.
square, yeah, exactly. Huh? So it's square. Actually, this is under the header of Malus law. I mean, with an apostrophe because it's Malus law. Huh? That's this one. So there's the relationship of the intensity of light going through depending on the angle of the Polaroid. Like Hainsworth basically goes back to our question B we had to some degree, right? That we say, well, if it's in the plane, that means there's zero angle. Again, it's a question of defining the angle. Theoretically, we could as well go from here, actually, right, and say it's a 90-degree perpendicular to the travel direction. But the law was phrased differently, so we don't change the law. And what will be there for the intensity now? When I take my cos square of 45 degrees,
0.5 squared.
y squared.
Because cosine 45 is 0.5. And then the square.
I'm just that's fine. I'm just looking at something. So to go back to the question, it's horizontal. When you have the just a second, Chris, I want to. Okay, let's go. Let's go here. So the cos of let's say 45 degrees. I mean, or we can as well say cos of pi Carter, huh? Because there's an easy table to memorize. That's what I would like to show you. So we talk about sine, we talk about cos, and we take the typical ones. That's 5 fields. Okay, so now and this is the angle. Huh? Here goes the angle. So we start at 0, then we take pi 6. There's a reason why I use the pi, because it looks like a sequence, huh? Kind of. Of course, it's 30 degrees. We talk about 45 degrees. We talk about 60 degrees. And of course, we talk about 90 degrees, but that's pretty obvious. That's pi quarter. That's pi third. And that, of course, is pi half. Huh? So you see, here is a jump, of course. Otherwise, it's 6, 4, 3, 2. Huh? Helps a bit. Now, what the sign? When we start here, we make it in green. What is the sign of 0, Chris?
0.
0, huh? Well, I want to have that in green. Oh, that's not exactly 0. Okay, and now instead of getting the value, what do you? This is like a numeric sequence then actually from the result of it. What is the sign of 30 degrees?
I remember there was a triangle to base off of.
Yeah, you can. Yeah, you can. But from a value point of view, I mean, as I say, I will not go into the decimal part. I will go into the fraction part. So I mean, in any case, but of course, but it is 0.5, huh? So the sine of 30 degrees is 0.5. Okay, is that okay? That's why the one we said before, that's why the number is different. And what we have is actually, the beauty of this is always half. And it's like then you have 1, square root of 2, square root of 3. So theoretically, of course, you could make it as well square root of 1 if you want to be like that. Then it's a very easy, and you just start with sine. You can of course start with cos as well, but this is nice because it's half square root of 2 divided by 2, square root of 3 divided by 2. When you take that value, how's the progress of the value if you would look at decimals?
Increasing.
Exactly. Huh? Why? Well, just from the basic logic of it, when you look at the development of the angle and the sine, what will be the value of sine at 90 degrees? Chris, just straightforward.
1.
When you look at 1, exactly. So I mean, basically, when you go back to our circle here, right, then you have the sine here. As it goes from 0, it grows, right? So you always have this. Let's do it in green. This is then the sine, right? So, or you go here, then you have sine. So clearly, as you can see, basically it's it grows in value. Here it's a little bit, and here it goes further, etc. Right. So that of course is there's some reason why we do it always like that. So we go counterclockwise typically, right? And then of course 180 degrees. So the sine is growing, and of course the opposite, of course, is then the cos accordingly shrinking, exactly the same. So when we now say this is 1, this is 1.0 actually. So if you would continue with that one, you could actually get this one, which of course is nothing else but 2 over 2, which is 1. So you can actually continue with that sequence from 1, square root of 1, square root of 2, square root of 3, square root of 4, always divided by half. So you have a nice sequence which helps you tremendously as you go into trigonometric equations. Then you will need that all the time, because typically the angles are then 30, 45, 60. So you can play around, kind of play around with this one, which will help you tremendously. You don't go into fractions, in decimals. That would be, well, we can make it either, or we can just calculate it divided by 2, right? So that would be 0.7 simplified, 0. So, and if you take the next one, 3 square root divided by 2, 0.867 or 87. So that, if you have a trigonometric equation where you have something like whatever, cos plus sine of certain angles, and you have to solve it for something, then these here, they will be useless. I mean, of course, not this one and not this one, but this one in between. So, but if you come with this one, then you can start to, of course, solve the equation much easier, because you have a value you can handle, which is then, for example, either multiplying with each other or dividing with each other, etc. So that's why I always recommend keep that in mind here. This one, of course, I can. This one is rather the other way around. So it's a bit like this one. That you can say this is 1, but we can as well say this is square root of 4 divided by 2, which is 2 over 2. Same thing here. Or we can say this is square root of 1 over 2. And what do you think will happen with the cos in terms of numeric sequence? When you look at this one, right, this is for the sine. So what will happen for that sequence when you think of the cos?
The opposite?
Yeah, exactly, right. So that's the beauty of it. You can just whoosh, inverse it, well, kind of inverse it, not in the traditional sense. So exactly, so you get 1, you get 0, and of course, exactly the other way around. So we can say half, 2, sorry, yeah, of course not. And square root of 3 over 2, huh? So it's exactly what goes up goes down, you may say so. So in this way, what goes up from 0 to 1, and this one goes exactly in the opposite down with exactly the same values. So that's why this is, you only, so if you ever remember that one, and just say, well, it's the square root of half, and it starts with 1. So it's 1, 2, 3, 4. Easy. And you have the typical angles of 60, 45, 60 degrees in between. When 0 and 1 are obvious. I mean, 0 and 90 are obvious. Huh? This is 6, 4, 3. So when you now are, and this is typical in physics then as well, for example, you have the typical 45-degree angle. What is that? Actually, the cos of that, and that's where it's the same. So that's where they meet at 45 degrees, as expected, actually. And half has to be a lower angle. That's not unimportant to remember somehow. That you would, half is not at half the angle. I mean, that's half, obviously, between 90 here. And then it's not half, but it's obviously exactly the same value for both at 30 degrees. That is, excuse me, I rephrase what I said. At 30, respectively 60, they're half. That makes, whereas the same values are in the middle. which makes sense. So they have to be, but that's not half in terms of value, but half in terms of angle, and you get then that value. So they are the same, doesn't matter in that context. So when you now get cos of 45, of course, is this one. Now, and when you say cos square, cos square of 45, what is this, before you calculate that, how do I have to imagine that? What makes it cos square, if you want to say so?
It's the result squared.
Yeah, exactly. I mean, the results there, or you may say as well, it's cos 45 times cos 45, right? I mean, it's the same as it would be a square, right? You just say a times a, of course, same thing. So henceforth, you can, of course, go to the result and just square it, like you said, huh? And when you square that, what do you get?
It's 2/4.
Exactly, huh? 2/4, which is how much? If you simplify it a bit. Because we don't want to leave it like 2/4, right? Yeah, just half, right? Or 0.5, huh? So that excursion was here to bring you a bit closer, because you will need that all the time, be that in physics or math, this typical 30, 45, 60, 90, of course, but 30, 45, 60 angles. And then this is very helpful to keep in mind. Just keep the sign, because this is the one which is growing, so to speak, starts at 0, becomes larger and larger. So from 1/2, square root of 2/2, square root of 3/2. And that is in many ways, in many cases, very helpful, because you will exactly have these angles, so you can start to simplify. You don't have to continue with the cos and the sine eventually, because that's usually, you will have, in the end, you want to have a result for the value, where that cos and sine is out of it. And that's exactly what you get here. Huh? So in other words, when we look at this cos square 45, what is there for the value now, Chris?
0.5.
0.5, huh? Exactly. So 0.5 times I0. And for the purpose of simplicity, or clarification, I call that I2, I3. Huh? Now, when I go after the third polarization filter, what will be the intensity of that one?
I think it remains at 0.5.
Yeah, that's a good question. When you look at what you have to do here is to say, okay, what comes through? Here is easy, right? Because you still have the same because of this one, cos is 1. But after this, so that's why this calculation is correct, but it somehow doesn't tell the full picture, because in the full picture, you will think of this one, right? Say, it's the result, but because the angle is 0 degrees, I get a 1, so it's times 1. But strictly speaking, for the purpose of clarity, I would have to say, well, it's this one times 1. Like here, 0.5 times the original intensity. So when I go into I3, I have this one coming out, that's this one, which is going into that filter. And how much would that be? And we have to think, and now this is a bit a tricky question, because we have to obviously figure out something that I can prove is not 0. Because if I would go straight forward, I would say, well, the angle is 90 degrees, so hence it's 0, but it's not. So what do I have to apply in terms of thinking, Chris?
Uh,
It's a bit, yeah, please.
the the plane is not. It's no longer covering the wave, so it won't the wave just go past it because it's not covering.
That means we would have zero intensity,
What?
right? According to what you say, which is fine. We are in the discussion, right? We have to consider because the when you go into one step, the point here is we have a two-step. I mean, ultimately three, but from what really counts is we have a two-step approach. We go from here to here, from here to here, which is not exactly the same as having it plane in here. So it's not going. If we only have it in the plane here, yes, that's a different story. But here we go and say it goes through various filters. So what we have to think of is the change of theta actually. It's a bit a tricky thing to consider. So here, that's why here we go in a 45-degree angle, and here we have another 45-degree angle of change. That is what we want to show here actually. So we have first of all, of course, we have the I2 coming in, right? From the previous one, this is the light I'm getting, or the intensity of light I'm getting from the second step, from this one. And then it's still a further 45-degree angle. I mean, I'm sure nobody will have that right in a test up front without having had that discussion. Because I'm sure quite some will challenge that. I think so. That you say, well, hey, wait a minute, but I have this angle original, then I have this angle, and then I have that angle. So isn't it that it's then like 90 degrees here? I say, that's true, but that's not the situation. So we have to separate what we typically think of, oh, okay, it's either like this or like that, but it's not. We have a step in between with this one, and as a result of each one, the intensity changes. And we have a movement, so we have a 45 angle here first, and we have another 45 angle then. Because it's like a transgression where we then move when we move down. And that means there is the one coming out we'll have from the second one is only in a 45-degree angle, not in a 90-degree angle. Do you see what I mean, Chris?
Yeah.
So that's something which is in the not really said at the theory. You only see that when you do such an exercise. That actually basically it's the delta theta you have to consider, not just the theta itself. So if you change the angle by 90 degrees, of course, then you have exactly that situation. So it's like this. But if we go with a filter in between, it's a different story. That's the trick. So we have a filter in between, and the filter in between will change the outcome of what is coming out of here. And then coming out of here means it's then hitting that one, not in a 90-degree angle, but it's in a 45-degree angle. And hence, it still applies like that. So it's like a double effect. Huh? And the double effect is then that we say, okay, we basically have 0.5 times IO, that was my O, that is this one, of course. And then I have same thing all over again, times 0.5, because it's a 45-degree angle. So which means, of course, then I have 0.25. That's my final result. So interestingly here, it looks like linear jumps, right? From 1 to kind of, or you can say half, as the angle halves. Huh? But that is actually the bottom line message here, as the angle halves. It's the same angle, but how to say it? In regards to the 90-degree angle, it's like half of that one, so it reduces it by the 45-degree angle. So it continues, so it's half of half, so to speak. Because first we go into this one. That's half coming out of it. That's what continues. And then what's coming out of it will be halved again, which is another sequence actually. So you get half, 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 half. Of course, at 90 degrees it's finished, so we can't continue obviously for that one. So that's why if you would have to indicate it on a simple chart, where we say, how does it go with the intensity? So obviously this would be my theta. This would be my reference point of I0. So make it a bit like 0 degree, 45 degrees, 90 degrees. Then clearly I have it like this. Sorry. So I have it here. My I0, then I have it at 0.5, and then I have it at 0.25. Huh? So and we can see a certain link between, it goes first here from 0 to 45, which means it halves, and then of course it makes another same angle, delta, so delta 45, delta 45. That means it has the same reduction effect, so another half, so times 0.5, and here times 0.5. Huh? That's why in many cases you can see that these physics people or chemistry, a bit less, quite often have a strong mathematical background, right? That's why they were so interested in sequences actually. As you can see, there's a certain link of how it develops. Huh? Okay so far, Chris?
Yeah.
Okay, all right. So keep in mind, it's the square, and the square is very straightforward actually. It means nothing else but, well, it's square, right? So you can look at it at the outcome of one angle and then just square it like this. Or you can think of, well, it's cos phi, cos whatever, times cos whatever again. Hence, then if it's the same angle, which of course it is, because that's why it's called square of the same angle, you can just square the result. And keep that in mind, because it's tempting, I know, that quite often 45-degree angle is being equalized to half, but it's at 30 or at 60, depending if you look at sine or cos. Huh? That helps a bit with this sequence. All right, then let's go. We look into transverse and also basically property of waves, and if when they differ, if you have transversal or longitudinal. And let's just start with this one. So this is one of those which, just to say as a brief side remark, right? Which of the following statements is correct? So yes, we have multiples of statements, but is correct. No? So it means clearly there can only be one. If it would say which of the following statements are correct, you could have a theoretical multitude. Maybe yes, maybe no. But the moment it says, you could as well say which of the following statement is correct, that would be okay as well, from a language point of view. But of course, this is the ultimate correct language way to say we have several statements, but only one is correct. This is basically the short version. So you can rely on that, but be careful. If you, for sometimes there's a possibility that more than one answer is correct. But that should be reflected in the question. Then it could not say which of the following statement is correct, then it would have to say which of the following statements are correct. Huh? It's a detail, but it can be the difference between 0 and 1 in terms of points. Huh? Okay, so which one is correct now and why? Or what information can you gain from the graph? Which then will be helpful to answer the question. Which, yeah, please, Chris, sorry.
330 divided by 2 times 10 to the power negative 3.
Okay.
Wait, no.
So that's why I'm a bit. I mean, you can go straight to the ones you know, the basic equations. I mean, the multiple choice questions are always a bit. You have to look at usually more than one equation because they cover different aspects. That's why they are always actually more complicated than they seem, to my opinion. The multiple choice, because you have to consider different angles before you can answer one. Sometimes it's very obvious, sometimes it's less. I mean, or you can just tick them off and say correct, correct, not correct, right? Let's go now. Can you say? Could you say something about B? I mean, what is stated in B? Can that even be said from what you see?
It's wrong.
It's not. You cannot, right? I mean, exactly, because it's not. You cannot say it actually. The displacement. Well, you don't know which type of display because it's displacement over time, right? So. Of course, longitude or transverse, they will both vary over time. So we don't know what type of displacement it is. Okay, then what about the frequency? Or how can I?
It's correct. The period is...
Okay, let's.
Oh,
When you
no.
okay, it's okay. Yeah. Why do you change? It's fine, Chris.
Because the period is 4 milliseconds.
Yeah, exactly. Very good. Exactly right. That's what you can get. The moment you have time, you can say something about the period. That's very important. Yeah. Whatever you take. So it's t is 4 seconds, right? Or milliseconds. It doesn't really matter. Sorry, but let's take milliseconds. Otherwise, you get a bit of confusion with the hertz eventually. Milliseconds, huh? Okay, so as I can say something about t, what can I say instantly therefore?
Frequency is 250.
Exactly right. So the moment I have t, I can talk about f, which is 1 over t, which is therefore 250 hertz. Huh? Or if I want to be very precise, 4 times 10 to the power of minus 3, which means I get 250 hertz. Huh? So Hainsworth, that should have been in green, but doesn't matter. So Hainsworth, incorrect as well. Huh? Now let's go to D. Obviously, probably, most likely A is correct. What about D? Is that true? The intensity will be doubled if the amplitude is increased to 0.4?
No, because
No, why not?
intensity is proportional to the amplitude squared.
Exactly, huh? And we have clearly this is double, this is double, so no, exactly. Okay, so by law of exclusion, we say A has to be correct, but of course now we want to cross-check that. How can I now, in terms of calculation, saying I prove it instead of just exclusion, right? I mean, one must be right, so that's the only one left. But if I come from the other angle and say, okay, now let's calculate it. How can I calculate that?
1.32 times 250 as the frequency.
Okay, yeah, okay, that's a good one. So we say so v is my f times lambda, right? So I can either use that one and then come back to the speed of air, or I just go the other way around, right? Say, well, I can, so this one, that's what I say, so to speak. I say v over frequency. And what you said is you do actually frequency times lambda, right? You take the value as it is, and hence we prove that this is the original value. Huh? And I go the other way around, right? I go, basically I say v over f because I have v. I have f calculated, hence I must get a lambda which must be identical. So two ways, right? Same thing. And of course originating from the same equation. Huh? Okay, all right. Two light waves, they travel at the same frequency. Now comes the phase difference. This is, yeah, let's see. So we have, well, we can call them A and B, for example, doesn't matter. A and B makes life a bit easier. And when you look at it, and usually it's easy to, well, you can start with any point, right? It really doesn't matter. But for simplicity point, you can actually start with this point and say, okay, A is at 0 here. And when will B reach 0? At which phase angle?
100.
100. So it's offset by 100, right? But is that now the phase difference or not yet?
No.
Okay. So how's the phase difference?
They have different wavelengths, so. Oh wait.
Nope. That's the point, right? They have different. What is the? It's fine. What is different between A and B actually? I mean, apart from the phase difference.
Only the amplitude.
The amplitude, exactly right. So they're the same. Otherwise, yeah. Well, theoretically, well, in this case, let's see. What is when you see the phase? I mean, of course, in the end, it's all 360 degrees to make a full circle. That's why it's difficult to say here because it's a phase angle, right? Of course, the complete circle has to be at 360 degrees, right? So from here, this is the starting point and comes back. That must be by definition 460 here, actually, because well, we're talking about waves. Huh? So that must be 460. It doesn't matter really, but just to say, right? So that they have different amplitudes. And actually, because it's at the phase angle we are looking at, we can't say anything else under this. So that's different. But are they really different or not? It's difficult to say, right? In that regards, the suspicion is probably not. I mean, sorry, the other way around. I would say probably yes, but the phase angle is purely about how they differ from each other. So they're just coming at different intervals. Could be the same wave at different intervals, actually. Now, how do we calculate the phase difference.
Should be just 100.
That's a tricky point, right? We have a phase angle of 100, but that's not yet the phase difference. That's the point. Because what we see here is the phase angle. That's not to be. It plays a bit with this one, which is fine. So we get more clarity. It's not that touched so much in detail in the book, actually. That's why the phase questions come rather in chapter 13 in more detail. But I think so. That's why this is a bit in between. So what we can say, it has a phase angle. They don't give it. So a phase angle of 100 degrees at displacement of 100. Huh? Of 0, I mean, sorry. So phase angle of 100. So the phase now, that is hence worth 100 minus 360 because it's offset. So it's minus 260. And hence worth, that's for B. Okay, so B. A has a phase angle of 0 degrees at displacement 0. Maybe better the other way around phrased, actually. Has a displacement of 0 is at although it's tempting to write it like in same sequence, here it makes logically more sense than say, well, the displacement of 0, because that's where the link is between the two, displacement of 0 at phase angle of 0 degrees. So that means the phase difference between A and B, so delta AB, is 0 minus 260, which makes it 260. So basically we calculate and say, okay, what is the phase angle when it's at displacement 0? I could take another one, but 0 is a good point, easy to see on the chart as well. So of course I could start with the curve A and say, well, it has a displacement of 0 at angle 0. And phase and wave B has a displacement 0 at the angle of 100. So that means it has a phase of 260 degrees. Also minus 260 degrees, excuse me. Because it's that 100 behind. And then the difference between the two, and that's the key point, right? You see, this is now the difference between these two, or if I would say, the one thing which I miss here, the phase is actually 0 degrees, huh? For this one. And henceforth, I can then come to this one and say, okay, what is now the difference between the two phases? That's, I think, the key point here to say when we talk about phase difference between two waves, we look at the phase of each wave separately. Typically, you would have always, ideally, you choose one which is already 0 at 0, right? Makes life much easier. So you only have to consider if that wave is now lagging behind, so it's the minus 260, or is it the other way around? Meaning it would look shifted to this side, actually. Then, of course, you would have the different effect. Of course, in the end, it's always a matter of where you cut off. You could as well cut it off here and then start and say, well, this one is at 0 and the other one is 0 then here. But it becomes more complicated to see. But in the end, you get the same result. Huh? Is that okay, Chris? Okay, so the phase difference between two waves is the difference of the phases actually of each of the waves. Now, this is another interesting one actually. With less, so you have a wave traveling at 24 meters per second, and it has a frequency of 15 hertz. What is when you have 2 points 2 meters apart? Is there a phase difference, yes or no?
Divided by 15.
Okay, so 24 divided by 15, right? And that would be 1.6 meter. So if I'm now 2 meters instead of 1.6, it's 2 meters. Huh? So 2 meter, 1 meter, and roughly 1.6. So when I now visualize so that means at 0.8, something like that. Huh? Okay. Would that be okay, Chris, for the wave?
Yeah.
Okay, and now if I now look at the 2 points here and here, or let's go back and say, what about these 2 points? If it would be at 1.6, would they be in sync? This one, this one. Also, I mean, the length of the wave, so to speak. They would be in sync, right? That's the key, the point here. But here now I'm 2 meters. So how much further away am I? That's probably the easiest way to look at. 0.4 meters. Henceforth, what must be the phase shift?
0.4 over 1.6.
Yeah. I mean, that's one way to look at it, right? The point here is the phase shift you can link with a very obvious physical dimension, meaning distance, for example, that you say, well, if it's 0.4 meters, then the phase shift is exactly that one. So it will be, or if I continue with my wave, actually, 0.4, then of course it will be exactly here, right? So in other words, when you look at it, it's at the max, it will be at 0 again, min, and 0 again. So it's actually exactly a Carter cycle of the wave, which means it's in a shift of 90 degrees. 90 degrees later, that's a bit the confusing thing sometimes, we can utilize that 90 degrees like a time factor, kind of. But we don't have to go into what is the timing of the wave, really. I mean, we can just say, well, if I know the wavelength, I can then take any point and accordingly out of that, define how that specific point is in sync or in phase difference to the wave, depending on which part I am, in which part I am. Huh? And that is very easy here, actually, then to see it and say, well, at that point here, it will be here, but it's in line with the wave, so it's exactly 90 degrees, or a Carter of a cycle. Which the wave, how much of the wavelength has been made, or of course you can say, well, that's identical to the period, right? There's no difference in that one. It would be a Carter T, right? Same thing. Okay, let me see. I think we've done enough of those. We can still do this one. Yeah, let's do one of those, the so-called hard ones, which sometimes they are harder, sometimes they are not. And what about this one? So we have two waves, P and Q. So that one is obviously one which has, okay. I have the amplitude and the frequency of P. So this one I know. So I should make that green actually. And so now what about Q?
For the frequency, so one period is about one period of VP of 1.5. No.
Okay.
3.
Okay, yeah, the other way around, huh? So TQ would be 3TP, like that?
Yeah.
Exactly right, huh? So this we can do very graphically, right? That you say, well, okay, that's where I am with my P, right? So I have 1, 2, 3, exactly. Huh? It's a simple count. This is, of course, quite so. This is just giving a bit how you can do actually something very visual in that regards. So, which means, what is the frequency Ainsworth? Of Q, huh?
3 times 100.
Oh, I think I wrote it wrong. Let me just. So we say one period of Q. That's the red one. No, the other way around. My bad. I was just thinking like this. Yeah. Well, because otherwise I was saying, yep, small detail. Otherwise you wouldn't get the 3 times. Because frequencies invert to the period, right? Ainsworth. And you want to know Q actually. Or like maybe you say it at the beginning. This one, of course, is not a bad idea either, right? I mean, either way. Then you get instantly the 3 out of it by inverting it, huh? So it must be 300, right? So the frequency of Q must be 3 times Ainsworth of the frequency of P, hence we get 300. That's one thing. So we only have 2 candidates now. And what about the amplitude? It's a bit guesswork, frankly speaking, because you can't calculate the amplitude really.
Which is 4.
4, right? Because it's either 4 or 2. Yes. I mean, and we can see from, even if we say, we try to draw some lines and say, okay, this one is more or less here, something like that. This one here. So that seems like half, right? 1, 1. So Ainsworth, it must be 4. Guaranteed not 2. It's a bit guesswork, but it's in the realm of what is possible, because here we only have discrete number of values, 4 and 2. So hence the drawing doesn't have to be perfect. Just it's good enough for the qualitative part. And that is clearly that we have a 2. The 1, 1, that means half. Ainsworth, go for A, huh? Okay. So see, that's what I mean. It's not necessarily harder than the ones before, actually. It really depends. And see. Okay, maybe we can do this one as well. So we talk about intensity of two different waves. This is intensity more math or mathematical physics intensity compared to the one with the graph. That was more intuition, right? This one is a bit more in the math side. How would you start with that one? How to solve that, Chris?
Find the ratio of
Yeah, good one, yeah.
Amplitudes.
Okay, all right. So we can say, and which one to which one? I mean, not that it really matters in the end. Then just otherwise the invert one.
Wave 1 on the bottom and wave 2 on the top.
Okay. Okay, and when we now talk about intensity, Hensworth, what can I equalize now? Or how do I make the link now?
The root of the intensity of wave 1 times the ratio and then squared is the intensity of 2.
Okay, all right, so let's do step by step. So we say like that. Like this? What's the first step, Chris?
I was thinking it's easier if we just square root the wave 1's intensity and times the ratio.
Oh, okay. So you would square the intensity.
Square root the intensity.
Ah, okay, sorry, my bad. Okay. All right, okay, yeah, can, of course. Let's do that. Would you square root each one individually? Or so like this? Or like that?
I think it's the same.
Okay, all right. Well, yeah, sometimes just to, yeah. All right. Now in values. And we want to know this one, huh? Just to make sure.
2.9 over
Oops.
1.9.
And then
Equals
I see. Okay. You could, well, it's even a bit. The drawing is a bit unfortunate actually. I would have said, you know, like really touch and really touch, right? But it's fine. Just to say, would rather have said 3 and 2. Okay, but that's fine, of course. But that would have, if somebody would have chosen 3 and 2, that would guaranteed be accepted as well. Okay, and then because you see with the square root, Chris, because you want to have I2, right? So in tendency, I would not square root that. but rather leave the square on those, because it doesn't matter. You just square the values. That's all there is. And you want to have the I1. Sorry, the yeah. I mean, I wrote it down wrong anyway here. Sorry, my bad. That should have been I2, and hence, of course, the color's different. So that have I2 and wrong. I1, this one, I2. Okay, so you see, you have to square it. So in terms of math, it's easier if you just leave the square because you have the values, right? 2.9 and I 1.9, or 3 and 2. You just square it. Then you don't have to square root it, actually. You know what I mean? Right, then you can go straight to I2. Otherwise, of course, it's the same in the end, but it's a bit easier way, because you are really not want to know A1 or A2. You want to know I2 as a result of I1, and of course A2 and I1, A2 and A1. So no square. So then rather forget about the square. That makes life easier, right? You don't have to reverse it again. Then you can just go straight and leave it. Basically say, well, if you go, let's say that's about the same as 3 over 2. Now we square it. So of course we can just say 9 over 4, right? Makes life a bit easier. And then, because we have done already the ratio, 9 over 4 times what, Chris?
Four, 4 point, no. 0.6 times 10 to the power negative 6.
So say again, please. Sorry. Times how much? Not as a result. Just with which value do you multiply it?
Just intensity of wave 1.
Yeah, exactly. Huh? So 1.6 and 10 to the power of minus 6. Huh? Now let me just check. So we say A2 over A1 makes I2 over I1. We want to have I2, so still correct. Oh, I think I see the wave 2 is 3, huh? Yep, and wave 1 is 2. Okay, just to make sure. Okay, so how much do we get? Or in other words, when you look at it, without any further calculation, 9 over 4, right? So this is like 2 and 1/4, right? So roughly, it must be something like 3.2 plus, I mean, actually 3.6, to be very precise. So what I want to say, without even using the calculator, you can just, and the good idea from you was, of course, to put it into the ratio. That is always very helpful in these type of questions. So make a ratio with what you can see in front of you, right? Amplitude. Then link it to the value you're interested. This is intensity. So of course, if you can have a ratio of the amplitude, then you can make as well the ratio of the intensity, because one is equal to the other when it's squared, of course. And then for the simplicity of the calculation, as you're interested in I2, then better don't going to the other way around, I would rather leave the square here. It's a different question, of course, if you are interested in the A, then of course, better do it with the square root if you would like to know A1 or A2, also the amplitude. But here we are interested in the intensity. Hence, I would rather go this way. Huh? Then you just, and then the ratio is the all. That's exactly what it tells you. It's the ratio. So it tells you how much is the second one. A multiple could be, of course, below 1, in this case above 1, of the original one. And the intensity, and does that match with our expectation? It does indeed, right? Because we expect, as the amplitude and the intensity are linked in a squarish dimension, so that's why if the, or in other words, you can say the amplitude is 50% higher from one to the other. So of course that, due to the relationship of the power, will have its impact accordingly on what you have as a result of the intensity for the second wave, huh? Because the second wave has a higher amplitude. That's the cross check. So it must be higher in intensity. It's very straightforward. If the question would be which one has the higher intensity, that would be a bit too simple, right? Because we can clearly see that this one has the higher amplitude than that one. So henceforth, of course, it must have the higher intensity. So sometimes it helps to simplify the question down to say, well, actually, regardless of any value, I'm asked about the intensity of wave 2. So clearly it must be much higher than this one because it has the higher amplitude. And of course, I know the relationship between intensity and amplitude. Henceforth, it's a matter of question of a ratio. So you had that without all that, you just came to it, which is very good actually. So I just phrase it a bit in the bigger context. Okay. We have more questions to those, and I would say we go one more into the electromagnetic spectrum, and I think this is an interesting one. So we have two lasers, they pass through a vacuum. The one is red, the other one is green. Which properties of the two lasers are different?
The frequency,
Okay, and why?
because the speed has to remain the same, so the
Okay.
wavelength and frequency change.
Exactly. So that is where we have a situation of change of frequency. And why can we say that? Because we see it's different lights, also what we see as different colors. So that means clearly as the color changes, henceforth the frequency is changed accordingly. Huh? Okay. Now we have nanometers, also typically wavelength of a laser actually. And now quite a simple question kind of, but interesting. In number of wavelengths that is traveled by light in 1 second. Yeah. So which equation do I take here in order to answer that question?
The speed equals wavelength times frequency.
Okay, yep. Right, so it's a bit like, which is another way to say the distance in number of wavelengths. So, well, of course, the number of wavelengths is actually the frequency. So how many times do you have a wave? You could as well say the number of waves. having completed the cycle. Sometimes these questions play quite some with the words, which confuses a couple of students for sure. Huh? Not you, that's good. So, Hainsworth, what is it? How do we get now the frequency? And how do we get the value? I mean, the frequency, I can write it down, of course.
3 times 10 to the power of 8 divided by
Okay.
600 times 10 to the power of negative 9.
Okay, okay. I would have written it like that, but it's fine. Makes my life a bit easier because then I can only have 3 divided by 6, right? And 3 divided by 6 is how much?
0.5 times 10
To the power of
1.
10 to the power of 8 divided by 10 to the power of minus 7. Don't forget it's minus 7.
Oh,
Exactly.
15.
Yeah, exactly. And then to make it a bit in a more user-friendly way, you can say as well, but it's not man. You can just say 10 to the 5 times 10 to the power of 14, right? And it really, of course, is the same. It's just because we have to put it then back into the answer, right? And see which one. So as they're all 5s, then I better make that in order not to suddenly have something with my power of whatever, huh? So yeah, just always careful sometimes, right? When you have the minus 7 underneath, which we have because it's 600 nanometers actually, then of course we actually add to the power in the end, huh? As we are interested in frequency, obviously. So of course the frequency gets much, much higher. Okay. All right, good. Chris, should I send you these 2 previous papers eventually so that you have it as a reference? Huh? Okay, good. And then we would continue next time. If it's okay with you, should we then already continue with the theory as well next time? Let's say we would go into superposition of waves. I mean, I would say probably half-half. I mean, we can do many more questions, of course, if, can fill the whole lesson next time. But maybe we could as well add a bit of theory. What do you think?
Yeah, we can. I think do some question and then start on the topic.
With some, okay, yeah, because diffraction is an interesting topic and it's very dominant as well, no doubt. And the whole wave behavior actually, in terms of when you have it as a continuation of the slit, basically an extension of the Polaroid. Huh? All right, then I'll do that. So I'll send you the 2 papers, and then I'll see you next Friday. Huh?
Yeah.
Okay. All right. Thank you. See you.
Bye.
Why is it that when I jump off the top of a moving train, I end up in a different spot? But when I jump up inside the moving train, I end up in a same spot. Is this what you actually do? Are you a stunt person for movies? So here's the thing. If the train is going by and you jump off of it, you are still moving forward along with the train until you hit the ground, then the train leaves you behind and you tumble. So you are moving with the train while you are airborne, okay? Well, watch for that the next time you do this. And of course, in the train, you jump up, you come down, the whole train carried you and your jump and everything with it, so you land in the same spot on the train. But from this ground, you took an arc. You hop. Yeah.
If someone deposited $200 billion in your bank account, what would your video start to look like?
Well, we are definitely at the point where more money does not equal more views. I can do a video titled, I gave a stranger $1 million, and I can also do a video titled, I gave a stranger $100,000, and it has no meaningful impact on the views. Past a certain point, the average human, it's like large sum of money, click. And like larger sum of money doesn't really impact the viewing experience. So, I mean, I would give it away and do stuff, but what people really want, which is what we're moving towards now more than ever, is like they want compelling stories. They want to get attached to the characters. They want to feel things that are intrinsic to a human, whether it be loved or wealth or power, these things. Like if you want to get 100 million views, they want to feel those feelings and watch a good story more than they want to see you just spend money.
If someone deposited $200
Nothing. Go Khan.
Over 10,000 people have died in Gaza already, with Israeli drone strikes